So I'm here on I would say beautiful Friday afternoon. At least it's not raining in central London at University College London with a real treasure in the world of cosmology, Richard Ellis, a longtime observational cosmologist and astronomer. And we've been discussing the recent Webb observations of the earliest galaxies. And you and I first met 23 years ago at Caltech. I was interviewing you for another article. And my first question to you in the interview, and I'm going to present it to you now, is what has changed in your career, in your observational astronomical career over in how you see early galaxies and what we most recently have learned?
So it's been an amazing 50 years, largely driven by technology. We've pushed the frontiers back to when the universe is only 200 million years old, and it's been a privilege to have taken part in a modest way in that big adventure. We've learned so much about how the universe evolves, and it's all really down to telescopes and new technologies, new detectors, and of course, hard work by a generation of observational astronomers.
And when we met, I think the paradigm was we had detected the first galaxies out to 1 billion years after the Big Bang. Now you're pushing it down to 250, 200.
Five times closer.
Five times
closer to the Big Bang, yeah. And we're beginning to see the glimpse of what we call cosmic dawn, the moment when the very first galaxies emerge from darkness. It's a fundamental quest because, we are made of the material that was synthesized in stars. So in a sense, we're looking at our beginning by pushing back to the frontier when the first chemical elements were synthesized.
So tell us how you think what's the theoretical paradigm for how these first galaxies formed and how large they are? Because when people think of the word galaxy, they think, large galaxies. But these early galaxies are really the sizes of what you said were globular clusters.
Yeah, so, as the universe expanded and cooled, then the hydrogen atom eventually formed, but the universe was dark. The gas clouds were there, but they weren't shining. And then, of course, the gas clouds were drawn into the dark matter, and the dark matter made the gas clouds collapse around them. And eventually those gas clouds got hot and ignited nuclear burning, and we see the first stars and star clusters. And these early galaxies that we're seeing with James Webb are physically very small. They're only tens of light years across, but they're producing stars 20 times faster than the Milky Way. So they're being seen at a remarkably youthful and energetic period in their activity. So joining up the dots between these early objects and the majestic spirals like the Milky Way and Andromeda spiral is, of course, the quest of galaxy evolution. And we've charted all that territory over the last 50 years in great detail with telescopes like Hubble and now James Webb.
And tell us about the quest for finding the first population 3 stars, what they are and how long they live and how they differ from the population 2 stars.
So, the original motivation for James Webb was to witness this cosmic dawn, to find a galaxy that was emerging from darkness for the first time. It's going to be very, very difficult. These stars that don't have the heavy elements, they only have hydrogen and helium. We call them population 3 stars, but they're very short-lived. The massive ones only live maybe 5 million years before they explode. And of course, once they explode, they pollute the gas with the heavy elements, so they're no longer chemically pristine stellar systems. So, we'll keep looking and we'll keep trying to find them, but it may be that we need to do statistical experiments and surveys to witness when this event happened.
And you actually were on the science definition team that put this request in to find the first stars for the JWST.
Yes, that's right. In 1995, I was the only European-based member of the HST and Beyond Committee, which was a committee that made the scientific case for what became the James Webb Space Telescope.
And let's circle back again. You started here at UCL. You taught at Caltech for a while, and then now you're back as a professor here. And let's tell us why, from an astrobiological sense. You know, a lot of money goes into astrobiology, and I think we both support, astrobiology. But in a way, you kind of talked about this at the beginning of this interview. In a way, without understanding the first galaxies and the first stars, we really we can't really get a full grip on astrobiology. Am I wrong in that?
Well, I think, the question of where the molecules come from, where the chemical elements come from, if you try to understand when this all began, then of course it's the birth of the first stars, because the stars develop these chemical elements in their nuclei, they explode, they produce dust grains, of course, as they explode. These produce gas clouds and dust clouds that circle around the next generation of stars. They may produce planets. Those planets, may eventually have conditions that are suitable for elementary life. And those elementary single cellular life forms formed, and eventually somewhere in the mix of all this, there's you and me. So, if you're really interested, if you're curious about science, wouldn't you want to know what triggered this all off? And the answer really is 200 million years after the Big Bang, the first stars emerged and the chemistry began its long journey to the complex objects like you and me.
So thank you so much, Richard, for your time today. It was a pleasure seeing you again. And I wish you luck with your continued research.
Well, great to see you again, Bruce. Thanks for coming to London.
Thank you.